Hi, good morning. So, in today's lecture, we are going to talk about Baire category theorem. Few of you had requested me to give a lecture on that. And except in the title, the word category will not be mentioned by me very much. Okay, the notion of category is not important to understand Baire category theorem or to apply. In fact, for applications, we are going to give two equivalent formulations. That's all you ought to know. In my something like 45 years of experience in this field, and mostly I'm an analyst and geometer also, I have never needed the category notion. I'm not saying that it may not be useful, it may be useful in set theory, but for practicing analyst for applications we don't need that. Okay, but forget it. So I'm sure you'll look at the statement, you will appreciate, and you will also learn why it's important and how to use it. That's more important, right? You will get it. Okay, so let us do that. But before we go further, I would like to give you some references. The first reference is my article, expository article, Baire category theorem and its applications. You can download it from the NTTS site given here, and it has very many applications, about 10 or 12 applications of various kinds. Okay, if you want to be a master in Baire category theorem, I think that's the best article to start with, because you really see how Baire category theorem is applied. Next time when you see anywhere, you will know, yeah, here Baire category will be applicable, I can use it. That is the kind of intuition you can build. And the next one is topology of metric spaces. Here again, essentially I followed the article, and okay, and with the experience, this may look slightly better than this earlier article possible. And also there are two forthcoming books of mine. One is with Dr. Sukumar on functional analysis, which is yet to be published. Due to COVID, it's being delayed. Otherwise, it should have been published by March, April. And there you will see Baire category theorem given a proof, and also its typical applications in functional analysis. There is also another book of mine coming. Okay, it's along with Dr. Santanam, Professor Santanam. That's an analysis on Euclidean spaces. There also I prove this theorem and apply it for context within this. So you can refer to them. At least 1 and 2 are easily available. 3 and 4 probably in the next few months time. So let us get started. So let us try to motivate how Baire category theorem addresses a problem I want to solve. So let us assume X is a metric space. Okay, I am looking for an element. Let me call it Z in X, such that Z has some property. It's a property P. Okay, maybe I am looking for a solution, and then Z is a solution, right? That's a property 1. Now in analysis, most often we may not be able to get the exact element to start with. What we do is we may look for a property Pn which is very close to P, okay, and look for elements which has property Pn. Let us call it Un. Un by definition is set of all x in capital X such that x has Pn. Okay, Pn intuitively is very close to P, right? Okay, and we also expect, again intuition, Pn, okay, approximates P. As n is very large, then I say Pn will be very close to P. That is, if x satisfies Pn, then it is as good as satisfying P. As good as, not exact, right? This way. Okay. Now, what the theorem says is, suppose, assume that Un is open and dense. What does dense mean? All of you know. If G is an open set, non-empty open set, then G intersection Un is not empty. for every non-empty open set should intersect UN. Then we call it dense. Okay, this is geometrically much better way of looking at density than UN closure equal to X. Okay, this is the best way. Right. So UN and UN. Okay. Then what it says is intersection UN is not empty. So let us go back. What I am saying, I want to look for Z which solves some problem. That's a property P. Then what I look for? I look for properties Pn which are very close to P. As n becomes very very large, I expect Pn to be very close to P. Then let us look at the set of elements X in capital X which satisfy Pn. Okay. Now I am further assuming my UNs are open as well as dense. Okay. Then what I expect is this the conclusion is intersection UN is non-empty. That means if you tell me Z belongs to intersection UN, since it's non-empty, that means Z satisfies Pn for every n. Therefore, I expect that it satisfies P. This is not P dash. Okay. So I have solved the problem. This is the basic idea. So essentially, this version tells you how to look for the existence of some element with some special property. Okay. Don't be worried if you understand about 40-50%. It's quite okay. As we go along, you'll see okay what it really means. Because unfortunately, too precise versions, you may miss the point. What the theorem is about. What are its typical uses? I'm trying to give that. Okay. Is that okay? Now let's go. Now let's look at just before this. Well, let U in X be open and dense. Right? Let F equal to X minus U. That is the complement. We want to understand the topological properties of F also. Right? So how do I do that? First, since U is open, I know F is closed. That is very easy. Right? Second, can any open non-empty open set, suppose G is not empty and open, can G be contained in F? Can it happen? Right? If G is contained in F, you see that now G is non-empty open, and you said U is an open dense set. Therefore, I know since U is dense and G is non-empty and open, what do I know? I know U intersection G must be not empty. That means there is an element X in U which is also in G. Right? That means X belongs to G. X is in U and X belongs to G. But G is contained in X minus U. That means X also belongs to X is not in U, a contradiction. So what have I concluded? I have concluded if U is open dense set, its complement is a closed set and its interior, because there is no open set which is contained in F. Okay. So its interior of F, namely, is empty. Remember, recall what is the interior of a set? Interior of set A is the largest open set which is contained in A, right? So what I have shown, let us just, this is the fact we had established, just go through it. U open and dense implies U complement, that is X minus U is closed and interior of U complement is empty. Okay. The converse is also true. What is the converse? Suppose I start F a closed set, okay, and such that interior of F is empty, then its complement, F complement, namely x minus F, is open and dense. Okay, the proof is easy. Since F is closed, F complement, namely x minus F, is open. This is all right. Now I have to prove it's dense. To prove dense, what is the definition? You are going to give me a non-empty open set. Then I have to show G intersection F complement is not empty. Suppose empty. What does that mean? G is contained in F complement, that is, it is contained, right? It is contained in F. Are you following? But G is a non-empty open set contained in F. That means interior of F is not empty, because interior of F is the largest open set contained in F, but G is already a non-empty open set which is contained in F. Therefore, interior cannot be empty. But that's a contradiction, because by hypothesis, interior of F is empty. Yeah. Therefore, what I have shown? I have shown that U, a subset of X, is open dense if only if its complement is a closed set with empty interior. Okay. Pause. Review. And then resume. See. So you have proved U in X is open and dense if and only if U X minus U complement is closed with the empty interior. So closed sets which have empty interior are known as nowhere dense sets. So closed sets with empty interior Okay, this is the definition of nowhere dense set. Okay, but suppose I give a subset A of X, when do I say it's nowhere dense? Okay, since so far I have defined only closed sets have nowhere dense property, therefore when I say A is nowhere dense, I want A closure, that is the smallest closed set containing A is nowhere dense. What does that mean? Therefore A is nowhere dense if and only if A closure has empty interior. You see that we arrived at the definition. Okay, it's not just like that thrust upon you. There was a reason why we started. Okay, when we went through, then we arrived at this definition. Is that clear? Right. Now let's look at a very typical example of a nowhere dense set, because students have problem with the A closure has empty interior. See, there is an equivalent definition which you can find in all four of my books, which I mentioned earlier, which is intuitively very appealing. Okay, I will explain that concept. Okay, suppose this is X, okay, and I say a set A as empty is nowhere dense. What does it mean is, you give me any open ball, open set, okay, then I can find another open set, small open set, okay, maybe inside this which does not intersect A. Okay, this is no problem, this doesn't intersect. But here it intersects A, but what I'm sure is I can find a small open set, non-empty open set, which is contained in the set, but it does not intersect A. For example, here. Right? This is the equivalent definition. Okay, and equivalence is also proved in all four of my references. You can look at it, but it's not important for what we are going to do. But this builds your intuition. Why it's very important is, if I look at something like Rn, okay, suppose this is Rn, and this is my space xn equal to 0. So this is the W, which is an n-1 dimensional space. Right? I claim this W is nowhere dense in Rn. Okay? Why? Look at this. Intuitively it's very clear. First it's closed, and start with any open set as I did earlier. Okay? I can always find a non-empty open set which avoids W beside this. This is your you gave me, and then I can find a V which is a non-empty open set contained in U, so that V does not mean to W. It is intuitively clear, right? Therefore, for example, if I look at any conic section, okay, suppose this is a conic section in R2, then I expect S to be nowhere dense in R2 by this kind of trick. Okay, have a look at it, understand. Now why it is closed is easy. Why W is closed? Let us look. X going to xn, this is a continuous map, and W is F inverse of 0, and singleton is closed, therefore W is closed. So it's a closed set. Okay, right. Now why it's, now remember, I want to prove it's empty. I already gave you, using my definition of nowhere density, I gave intuitive reason why W should be nowhere dense. But let's look at our definition. The standard official definition is A closure has empty interior. Right? Okay. Now since this is closed, W closure is W itself. Therefore, I only have to say it is non-empty. It has empty interior. That is also easy. Why? Suppose B XR, suppose it's empty, it has non-empty interior, there is a non-empty open set, therefore there is an open ball which is contained in this. You understand that? U is no non-empty open set which is contained in W. If X belongs to this, then there is an open ball which is contained in W. That's a matrix topology. Right? Now let's look at this set BXR minus X. This will be B0R. Right? Check this. Okay. So I have this, and here you gave me some BXR. By translating this by minus X, I am going to get B0R. Okay, this is my B0R. Now you give me any non-zero vector in Rn, then let's look at V by norm V and to R by 2, then this belongs to B0R. So given any non-zero vector, okay, there is a multiple of V which belong to B0R. Now B0R is contained in W, this is a vector space, vector subspace. Therefore, if I multiply this by suitable scalar, it follows that V also belong to W. But B is any arbitrary vector in Rn, and it belongs to W, that W says W is Rn, a contradiction. Okay. So this is an example. Spend some time, pause, review, then proceed. Okay, now we are ready to state the Baire category theorem. Okay, what does it say? There are two versions. The textbook will talk about a complete metric space is some category, I don't remember what it is, or some other book may say a complete metric space is a Baire space. If you learn Baire category theorem like this, you may not be in a position to apply. You may not even understand what is happening. Okay, so we are going to give two formulations which are very powerful, and that's the way Baire category theorem is applied anywhere in analysis and topology. Okay, so the assumption is let X D be a complete metric space. The crucial thing is this completeness. Okay, the first version says let for every n un be open and dense. Then intersection un is not empty. Of course, open and dense in X. Okay, notice that this is the way we started. This is the way we started. Yeah. Right. Okay. And the second formulation is equivalent formulation. Let for each n Fn be a closed set with the empty interior. Now that we have learned the jargon, we can say that is Fn is nowhere, closed to nowhere density, closed nowhere and nowhere density. Then union Fn cannot be equal to X. So again, intuitively, what does it say is a countable number of thin sets. The classical word for this may be meager. Okay, I use the word thin. Okay, whatever it is. This is a, for intuition, it's a good enough for me to think of thin word. See, for example, let us look at, just now I proved an n-1 dimensional vector subspace of Rm is nowhere dense. So in particular, if you take R2, right, you start with any line, then it will be nowhere dense and also closed. What the theorem says is R2 cannot be a countable union of lines. That's what the second theorem says. Okay, so both theorems you should understand intuitively first. It says the first version says, okay, you want to find an element with certain property, then what you know is look at UNs, okay, set of all elements which are very approximately, they have approximately equal property. Then suppose they are open dense, then this intersection is non-empty. That means it allows me to prove the existence of an element. The second version, what does it say, is that a countable number of thin subsets of a complete metric space, okay, their union cannot be X. Okay, again that intuitive example you should have is countable number of lines in R2, their union can never be equal to R2. Or countable number of planes in R3 can never be equal to R3. Okay, this is the intuitive example you should have in mind. Okay, The first observation is 1 and 2 are equivalent. Why? Remember, you had already said if UN is open dense, its complement, call it Fn, that will be closed and with empty interior. You understand that? Yeah. Therefore, if I assume 1, 2 follows. Why? So let us see, 1 implies 2. Why? Suppose you give me Fn which are closed and Fn interior is empty, right? Then let's look at UN to be Fn complement. We had already seen then UNs are open dense. Therefore, intersection UN is not empty, right? Therefore, take the complement. So take the complement. This complement is union Fn. This complement is X. So you get the result, and you can retrace. Similarly, you can argue. Okay, I leave it as an exercise. It's very easy. Taking complement, you are going to say 1 and 2 are equivalent. That's because we can make use of the earlier fact. A subset U is open dense if and only if its complement is closed and with empty interior. That's the only observation we needed. Okay. So now we want to prove this. So we will prove version 1. Okay. So it's enough to prove version 1. When we want to prove 1, again something very interesting is going to happen. What are we supposed to show? You are given UN to be a countable collection of open dense sets. You wanted to prove their intersection is not empty. What we are actually going to prove is something fantastic. Intersection is dense. It may not be open, but it is dense. Okay? What? So try to understand. Let's do that. Okay? Suppose U is open dense and B is also open dense. Subsets of X. Then I claim U intersection U is open and dense in X. You understand why? First, it's open, that's very clear, right? And can it be empty? It cannot be empty because U is open dense and B is open dense. That means none of them is empty. Therefore, U is dense and B is non-empty open set. Therefore, U intersection V is non-empty. Or other way around. B is dense, U is a non-empty open set. Therefore, intersection cannot be empty. Therefore, this is not empty also. Right? Now, suppose G is any open set, non-empty. Then to prove this is dense, U intersection V is non-empty. What do I have to do? I have to take U intersection V and intersect with G. I have to prove it's not empty. I have to check this. But that is very easy. Why? U intersection V intersection G, I can write it like this. U, whichever way you want, doesn't matter. Look at this. Now, what do I know about this? This is non-empty. Just now I said G is non-empty, B is dead, therefore this is non-empty. And this is open, therefore this is not empty and also open. You understood? Therefore this is a non-empty open set. Now U is dense. Therefore, when U intersect with any non-empty open set should be non-empty. Therefore this is not empty. So obviously it generalizes to up to finite things. If U1, U2 are open and dense, then U1 intersection U2 intersection UN is open and dense. Okay. This is not strictly not necessary part we want to do, but whenever you learn something, you should kind of explore. Okay. When you go to visit a place, you should not be only the important things, okay, places of interest, but you should also look around, appreciate the ambience. Okay, you explore nearby places also. So Look at that. We want to show countable intersections. Okay, this may not be open, right? But what we want to say, it's non-empty, it's dense. Okay, it's therefore in particular it's non-empty. And why we expect in some sets intuitively, if I take finite number of open dense sets, their intersection is open and dense. Therefore, a countable collection may be dense. Intersection of countable collection may be dense. It may not be open. It's just intuition. It's not a proof. In fact, we needed completeness to prove that. Okay, let's start with the proof. Okay, this is now actually proof starts only now. So what do I want to claim? I want to prove intersection union is not empty, but I set out to prove intersection union is dense. That means you are going to give me an open set V, a non-empty open set V in X. I have to prove V intersected with intersection union is not empty. In particular, since V is open, it's enough if I prove give me any B, A, R in X, then I have to prove, I want to prove B, R intersection union is not empty. So that means any open ball intersects this set. That means intersection union is, if I prove this. So if I prove, that would imply the intersection union is dense. In particular, this implies intersection union is not empty. Okay, good. So let's look at BAR. The proof is very easy. Unfortunately, I don't know whether I can draw good pictures on this. Even writing is a little difficult here, but anyway, let us see. Let's look at BAR. It's an open, non-empty open set, and let's look at U1. What do I know about U1? This dense set. Which is also open. I will use it later. This is a dense set. Therefore, this intersection is not empty. But it's also open. Okay, this is not empty. That means there is an X1 which is in BAR intersect with U1. Right? Right. But this is an open set. This is also an open set. Therefore, this is also an open set. Therefore, I know there exists an R1 positive such that Vx1 R1 is contained in BAR intersection U1. Yeah? Do you have some kind of picture? So I have U1 and this may be my BAR. That means there is an U1 X1, therefore R1 this is contained. This is my Vx1 R1. Right? Now I can as well choose my R1 to be less than half. You can choose. Okay, if R1 is already less than half, I don't have to worry. If R1 is greater than or equal to half, I just have to choose some number less than half, right? You understand? If R1 is greater than or equal to half, then Vx1 half will be contained in Vx1 R1. Therefore, I can as well assume R1 is less than half. Okay? Right. So I got Vx1 R1 and R1 is less than half, and just that this happens. Right? Now let's look at that. Now let's look at Vx1 R1. This is contained in this, right? Now let's look at U2. Now this is non-empty open set and U2 is dense. Therefore this intersection is not empty. Right? Now imagine the same picture. Okay? Call this as U2. Okay? This as Vx1 R1, Therefore, there exists an x2 here, and this as x2. Right? Now, x2 belongs to this, but remember this is an open set. Therefore, what do I know? There is an open ball B x2 R2 which is contained in B x1 R1 intersection U2. Remember, B x1 R1 is already contained in VAR U1. Therefore, this is actually contained in VAR intersection U1 intersection U2. Is that okay? So what I am saying, imagine the same picture. This is my U2, this is my BX1 R1, and this is my X2, and this is my BX2 R2. As earlier, I can again assume, again, we can choose an R2 so that R2 is less than 2 to the power minus 2. That is 1 by 2 square. Right? Okay. Now we want to proceed by induction. Let us assume that this is induction hypothesis. Assume I have chosen x1, x2, xn. Okay, and with what property? Xn belong to B xn minus 1 or n minus 1, right? And intersect with un, and also I choose, is it clear? And choose an Rn and say that each Rj is less than 2 to the power minus j, and say that Bxn Rn is contained in B xn minus 1 or n minus 1 intersection with un. Understand? The same picture we are going to do. Now by induction we had already seen this fellow is contained in VAR intersection with U1 intersection U2 intersection UN, like this. The next step will be Bx3R3 which is contained in Bx2R2 intersection U3, but that in turn is contained in VAR intersection U1 intersection U2 intersection U3. Are you following? Please pay attention, learn that. Is it okay? Now you have got everything, right? Therefore, now how will I choose my xn plus 1? That is, now let's look at B xn and say that Rn is also less than Bxn Rn intersection Un plus 1, and this is a non-empty open set, this is a dense set, therefore there exists xn plus 1. And again, therefore there exists a one open ball Rn plus 1 which is less than 2 to the power minus of n plus 1. So that Bxn Rn, sorry, Bxn plus 1 Rn plus 1 so that Bxn plus 1 Rn plus 1 is contained in Bxn Rn intersection Un plus 1. But by induction hypothesis, this fellow is contained in VAR intersection U1 intersection UN. Okay, this. Okay, this guy is contained in this guy. Okay, and intersection with UN plus 1. So by induction hypothesis we are done, selected a sequence xn so that xn belong to Bxn minus 1 Rn minus 1 intersection Un, and there exists Rn so that Rn is less than 2 to the power minus n, and Bxn Rn is contained in Bxn minus 1 Rn minus 1 intersection Un, but that in turn is contained in VAR intersection U1 intersection U2 intersection Un. Okay, so by induction we have selected this. I am not going to write that. Please pause, review, and proceed. So I found a sequence xn. Now what I want to claim is this is a Cauchy sequence in X. Since X is a complete metric space, then I will know Xn converges to X. That X I am going to claim is going to be common to Baire intersection union. Okay, that is our strategy. Yeah. Now first things first. Let us look at Xn. I want to show it is Cauchy, right? This you must have seen in analysis, even in first course in analysis. That's the same trick. So let's look at n strictly greater than m. Let us look at then b dxn. I have to estimate. I have to show it goes to 0 as n and m become very large. Okay, these are very small when n and m are very large. That's what Cauchy nature means. But this one is less than or equal to dxn triangle inequality xn minus 1 plus d xn minus 1 and xn minus 2 and so on plus d xm plus 1 and xn. Right? Now notice that by our choice, where does my xn lie? Xn lies in b xn minus 1 rn minus 1. Therefore, what is the distance between xn and xn minus 1? That will be less than rn minus 1. But what was my assumption about rn minus 1? That is less than 2 to the power minus of n minus 1. Right? Each rj is less than 2 to the power minus j. Therefore, this is less than or equal to, I have something like this, 2 to the power minus k, where k runs from m to n minus 1. I hope I am right. Yeah. Right? Yeah. Now what do I know? I know this geometric series 2 to the power minus k, n, okay. 2 to the power minus k from 0 to infinity if you want. This is convergent. Okay, and this is the partial sums of the series Sn minus 1 minus Sn. Right? Since this is convergent, the partial sum must be Cauchy. That means Sn minus 1 Sn must go to 0. Right? Therefore, what do I have concluded? I have concluded d of xn xm can be made less than epsilon for n and m sufficiently large. That means this xn is Cauchy. I hope you understand the proof. Maybe I will make a pause, review, proceed. Now, therefore, xn is Cauchy and x is complete. Therefore, what do I know? I know that there exists an x in x, that xn converges to x. Okay. Now we want to claim my x belong to un for all n. The way I want to prove that, look at this. If I want to say x belong to un for all n, it's enough if I prove x belong to b xn or n for all n for this ball. You understand this? If I show x belong to b xn or n for all n, then that automatically it will say that x belong to un for all n. Yeah. Now how do I show that? This is where an interesting thing comes. Okay. Now let us look at the first thing I want you to observe is, let us look at xk where k is greater than or equal to n. That is xk. Assume k is greater than or equal to n. Do you see that xk belong to b xn or n? for every k greater than equal to n. Do you see this? Why does it happen? Again, go back. By our construction, you can see my BAR contains BX1 R1, that contains BX2 R2, and that contains BXN R, right? Yeah. So by our construction, okay, B xn Rn is contained in B xn minus 1 or n minus 1, etc. That is contained in BAR. You follow that? Therefore, this sequence xk for k greater than equal to n, this is a sequence where in, I can think of it as a sequence in Bxn Rn, and this sequence xk or converges to x where the k is greater than equal to n. Okay, this converges to x. Now this is a sequence in this space and xn converges to x. I want to say x belongs to Bxn Rn. Can I say that? No, because this is an open set. This is a sequence. Okay, this is a sequence in this open set and it converges to x. X need not be there. But what do I do now? If somehow I know this is a closed set, I will be happy. But this may or may not be closed set. Right? This may or may not be closed set. But I can do something wonderful. What I can do? Let's go back. See, this is what you miss in textbook. They will start from the beginning something, so you are led by nose. You just verify things work out properly. The proof is rigorous, but you don't know how you modify the proof. Okay, let's go back. So let's look at the first step. What did I do? I said BAR intersection U1 is non-empty. Therefore, there is an x1 in this intersection, but the intersection is open. Therefore, I said there is an open ball Bx1 R1 which is contained in BR. Right? Do you see that? By cutting down the radius, okay, I can, instead of R1, I can choose some other row so that row is less than R1. And since already R1 is less than half, row will also be less than half. But B x1 row, call it row 1, that will be contained in this, right? In other words, what I am saying is, from the beginning, we could assume the following. Namely, there is an R1 so that R1 is less than half, but the closed ball, this is the closed ball. This is my notation for closed ball. Okay, the closed ball itself is contained in this. But the next step when I do, I am not worrying with the closed ball, I will take the corresponding open ball. Right, Bx1 R1 open ball intersecting U2, this is non-empty open. Okay, and therefore there is this x2 belong to this, and therefore again I know there is an open ball Bx2 R2 contained in this. But here again, by cutting down R2, taking a smaller R2 if necessary, I can assume the closed ball is contained, right? So therefore by induction I can assume there is an xn so that, okay, given an xn, I can choose an Rn so that Rn is less than 2 to the power minus n, and the closed ball Bxn Rn is contained in this. Have you understood this? Sure. Now let's come back. So I will not talk about xk as a sequence in this, but I will think of it as a sequence in E of xn Rn. Now I know this is a closed set. Any closed ball is a closed set. Now xk for k greater than equal to n is a sequence in this closed set which converges to x. Therefore my x, so this may be false. But what do I have is, this implies x belong to p xk or k. But remember that is contained in my bxm rn. But that is contained in un by our construction. You follow that? Therefore x belong to un for every n. And remember by my choice all these closed balls be xn rn intersection u1 intersection un etc. It's also contained in va, right? Therefore x also belong to va. That implies therefore b a or intersection un is not empty. So what does that say? It says that if I have open dense sets un, their intersection is dense. You wanted to prove only non-empty, but you proved it's dense, something which is stronger. But the equivalent statements, I don't want to say it's dense. You understand that? Even though I proved a stronger result, I didn't want to say then intersection un is dense, because then these two may not be equivalent statement. So here I only say it is non-empty. Okay, right. Now just as before we close, let us look at it. Let us look at Q with a discrete topology, discrete metric. Okay, all of us know Q is countable, right? And any discrete metric space is complete. Right? And here, and in any metric space, singletons are closed. Therefore, I have written Q as a countable union of singleton closed sets. Does it contradict? Baire's theorem? No, because since it's a discrete metric space, this closed set Xn, okay, as non-empty interior, because this singleton is also an open set. But by our assumption, what should we need? We want it to be empty interior, but this does not have empty interior. You follow that? One more. Now suppose I have Q, I am looking for a metric, that there exists a metric D on Q with two properties. One, the topology on Q, the D topology on Q is same as the standard topology on Q. That is the topology induced by absolute value metric. Right? You understand the question? Okay. Absolute value metric induces a topology on Q. The D also induces a topology on Q. Therefore, I say U is going to be open with respect to this absolute value metric if and only if U is going to be open with respect to the D. Is that point clear? Good. Second thing what I am demanding on D is complete. So question is, there exists a symmetry. What is your answer? Think about. Can I imitate this argument? If I can't, why I can't? Think about. Okay. And as I said earlier, for example, R2 cannot be equal to countable union of lines. These are the typical examples. And the first formulation, namely in terms of open tensor, this is used in the okay, in proving the existence of everywhere continuous and nowhere differentiable functions. Okay, there what you do, you construct functions with the slope arbitrarily large at various points. That is your union. That will be open dense. Then the intersection will be more or less intuitively believe at every point the slope will be infinite in some sense. That means the derivative does not exist. That's roughly the idea. You can look at my book on topology of metric spaces or the article, Baire category article for the details, or you can consult any other book for that matter. I hope you enjoyed. Please remember to mark likes, okay, and also write comments whether you liked it or not. These are the things which will keep me motivated to release more videos which may be of use to you. Okay. So thank you very much. I hope all of you enjoyed. Okay. Have a good day.